Hello, in this video we're going to be talking about Newton's laws, a few of them, namely the first and the third laws. We're actually going to save the second law for our discussion of momentum, which will be coming up. The IB loves to ask you about Newton's laws, and rightly so. They kind of are the foundation of all of the mechanics that we learn about. Just for fun, here is Newton's first law as written. Every body preserves in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. Whoa. What does he mean? This you've probably heard as an object in motion stays in motion, an object rests stays at rest. That's what we're really saying here. And unless a net external force acts on the object. So something that's moving wants to keep moving. It wants to keep moving forever and ever and ever unless another force slows it down. This can be a little counterintuitive because there's friction on Earth. So we're used to something moving will eventually come to rest. But that's only because of the force of friction, or maybe air resistance or something like that. In space, if you throw something, it's going to go forever and ever 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 and continue to move with a constant velocity. There's a special term we have for this kind of motion. We call it translational equilibrium. Translating means to move in a straight line. That's a pretty specific physicsy term and way to use the word. But to translate means to move in a straight line. So translational equilibrium means moving in a straight line at the same speed. All right, so constant speed in a straight line. Zero, like at rest, would count. That'd be a constant speed of zero. So it's another kind of way of saying not accelerating. So if no net force acts on a system or on an object, that object is in translational equilibrium. It will stay in motion if it's in motion, or it will stay at rest if it's at rest. All right, the second law, just to look at it, was written that the alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. We will talk about what specifically Newton means by motion in this unit as we start talking about momentum. However, you want to know that F equals ma comes from Newton's second law. However, this is not exactly Newton's second law. We'll hammer out how you can write out Newton's second law in variables. This is not Newton's second law. In a lot of places, you're going to see this written as Newton's second law, and it's like most of the time what you get when you use Newton's second law, but that's not quite right. The IB will surely not take this for Newton's second law. That's not quite specific enough. Right, you'll hear that in a lot of places, even in college and stuff like that. You kind of, in a loose way, call this Newton's second law as F equals ma, but it's not really. All right, so be careful. But the third law is the one we're really going to talk about, and that is written like this. To every action, there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. Again, that is a fancy way of saying every action has an equal and opposite reaction. This is how we usually say it in today's parlance. We talk about actions and reactions, and when we talk about that, we mean forces. This is a more thorough way to say it, maybe. If there's a force acting on object A, then object A exerts a force equal in magnitude in opposite direction on another object B. So if you push on something, it pushes back on you the same amount. This is two forces on two objects. A very good way to think of Newton's third law is like this. The force of object A on object B is equal to the force of object B on object A. They have the same magnitude and opposite direction, so we use a negative sign here. When you're doing a Newton's third law problem, you have to identify the two objects that are acting, and there can only be two objects when you talk about this. Many students have a lot of trouble with this because you're used to a free body diagram where you're looking at all the forces on one object. This is not at all the same thing. This is two forces between two objects with the forces on each other. What you usually think of as balanced forces are not action-reaction pairs. So we're going to look at some examples of action-reaction pairs to hopefully help you out. be very careful. You have to be able to write it like this for it to count as a Newton's third law action-reaction pair. All right, so here's a good example of you. This fine gentleman is pushing on a armchair and is trying to maybe move it, and so there's a force of this dude pushing on the chair, right? So he is pushing down and to the right on the chair, and Newton's third law would say there's an equal and opposite force of the chair pushing back on the dude, and that's what you feel whenever you push something. You can't feel your own force. You can only feel the force something pushes on you. So if you try and push like the desk in front of you or whatever, as you push on it, you should feel a pressure on your hands. That is the object pushing back on you. That's what you feel. And those forces are equal. They have to be. That's what Newton's third law says. If the dude pushes more, the chair will push back more. If he pushes less, the chair will push back less. Now, the difference is the chair probably has less mass, and maybe his shoes have a little bit of a better grip with some friction. So this force is able to move the chair, but the force does not move the dude. But it is the same force. Let's look at some other ones. Here's a good one. If you are a swimmer, or just like watching the Olympics or something, when a swimmer does this cool underwater flip and kick off of the wall, the idea is you're providing a force to yourself, and what you're doing is pushing against the wall so that the wall pushes on you and pushes you forward. Right, so the idea is by kicking and pushing against the wall will push back an equal amount on the swimmer, and that provides a thrust so that you get a little extra boost and you can, start your swim forward. So that's the idea. Notice again, it's two forces on two objects. If we were doing a free body diagram, we would only draw all the forces on the swimmer. We would not draw this force because that's a force on the wall. But in this case, when we're looking at Newton's third law and these action-reaction pairs, it's two forces on two different objects. The force on your feet, the force on the wall is the same. If you punch a wall, the force of your hand on the wall is the same as the force of the wall on your hand. But then the wall is much, 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 much more massive than your hand, and so your hand gets hurt, the wall not so much. This is the idea. One more. If you are canoeing or operating any kind of boat where you need to use a paddle, this is the same idea. The only way that you can get this boat to move forward is if you push backwards on something, and what you push backwards on is the water. An oar or any kind of paddle works by you pushing backwards on the water, so the water pushes forwards on your paddle while that happens, which makes the boat move forward. All right, so these are all force of paddle on water equals force of water on paddle. Force of feet on wall equals force of wall on feet. Dude on chair, chair on dude. You have to be able to do that for a third law question. So here's a good, very, very common one that almost everybody always gets wrong. You're sitting in your chair, the force of gravity pulls down on you. What force is equal and opposite to your weight by Newton's third law? Take a second, pause the video, and try and think about applying what we just said to this. All right, if you chose B, that is the most common wrong answer. You're introducing a third object if you choose B, and with B, you would be saying the normal force is equal to your weight. The force of the chair upwards on you is equal to your force of gravity downwards. Those might be equal if you're sitting at rest, if like your feet aren't on the floor, but that's not a law of nature that those two forces have to be the same. Someone could come around and take your chair and lift it and flip it and knock you upside down, and then the force of the chair on you would be much bigger for a moment than the force of your own weight. Or you could just stand up off the chair, and then the force of the chair on you is zero, but you still have a weight. Newton's third law, action-reaction pairs are always, always, always fundamentally the same force no matter what, because it's the force acting between two objects. So we need to identify what two objects there are when we say force of gravity. And the two objects are you and the earth. The force of gravity is the force of the earth pulling down on you, because you both have mass. And so the opposite would be you pulling upwards on the earth. That is the equal and opposite force. So whatever your weight is, if whatever your weight is when you stand on the scale, that's how much force the earth pulls down on you with. You pull up on the earth with that same force always, all the time, because of gravity. To the earth, that doesn't make a big difference. The earth is very, 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 very big. But you are pulling up on the earth, believe it or not, all the time. So that's how you have to format these third law action-reaction pairs. They can be tricky, but if you break it down to that format every single time, you will always get them right. All right, so there's the first and third laws, and we will very soon investigate the second law as we get into momentum. Have fun.